Hi, hello everyone. This is your educator, your tutor, your friend Sanjay Vishwakarma. I welcome you all to yet another session of We Learning. We Learning is a platform which focuses on providing right to quality education for all. Do watch this session. If you like it, do press the like button. Share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Okay, you can also visit our website, that is www.v-learning.in. You will get all the classes there. Along with that, you will be getting lecture notes also and a lot more. Go check it out. All right. Now, without any delay, let's get started with today's session. We were doing electrostatic potential and capacitance, and this is lecture number 9. In this lecture, we are going to see capacitors. This thing we are going to start today. All right, introduction to capacitors, and then we'll be seeing spherical capacitors. There are a lot of kind of capacitors, right? In your course, the capacitors which you have is parallel plate capacitors. That will be starting in the next session. For now, I'll be telling you what are capacitors, what is capacitance, why do we use capacitors, and then initially spherical capacitors came into picture. Then there were certain problems in those spherical capacitors, because of which we came up with a lot of changes happened, and finally we came up with parallel plate capacitors. Okay, all right. So now, what are capacitors? I already told this when I was teaching conductors, electrostatics of conductors when I was teaching. Capacitors are nothing but conductors. Capacitor is something which can hold charge in it. Why do they hold charge in them? See, there are certain devices, certain appliances like fan, or you can say electric motor, the motor which is there at your home which brings water from ground to the overhead tank, right? All these appliances, to get started, they need a lot of electrical energy. They need a lot of current. But for running, they do not need a lot of current. For running, they will need normal amount of current, which is anyways provided to them. But for starting up, they will need a lot of current. So now these capacitors are the ones which provide them a lot of current all at once. Okay, sometimes you would have seen at your home, when you switch on the fan, if the fan is very old, it does not start on its own, right? Then you take a rod, you push it, and then it starts rotating, correct? So what I'm telling is, for running they don't need a lot of current, but for starting up they need a lot of current. From where do they get a lot of current? Because if you see battery will convert chemical energy into electrical energy, but it will provide current in a steady rate. It will not provide suddenly a lot of current, right? It will provide current in a steady rate. So for providing a lot of current, we need something which can hold a lot of electrical energy into it. Right? So this capacitor is something which holds a lot of energy into it, and when needed it will supply a lot of energy all at once. The device will get started, and then the normal current will make it running, will keep it in a running mode. All right, you would have seen in your fans, sometimes when the fan is not working, when you switch on, your dad would have told you to get the condenser from the shop, right? Like this, you would have seen a cylindrical thing in your fans. In your ceiling fan, like this, one cylindrical thing will be there with 2 wires. They call it condenser. This is what capacitor is. Okay, when this does not work properly, then only your fan doesn't start and you need a rod to push it. Okay, then we need to change this condenser. I hope you got what is capacitor. Capacitor is something which can hold a lot of electrical energy with it, so that it can supply all at once when needed. So how does it hold a lot of energy? By holding a lot of charge. We are talking about electrical energy. Electrical energy comes from electrical charge, right? So if it holds a lot of charge, that means it is holding a lot of electrical energy. If you want, you can note down the definition. Okay, this definition is for the next session, when we'll be talking about the parallel plate capacitors. This is from your NCERT. Okay, the first line, that's why I mentioned here, a capacitor is a system of 2 conductors separated by insulators. Okay. We'll see this definition in the next session. For now, capacitor stores electrical energy and supply all at once. This is true always. Capacitor stores electrical energy and supply all at once. And how does it store electrical energy? Electrical energy is stored by storing charge. So both the things are correct. Capacitor, you can say it holds electrical energy. It holds electrical energy. Or you can say, or holds charge. Fine. This is the main thing. Holds electrical energy. You can also say it holds charge. All right. Now, capacitor, every conductor will be having different capability of holding the charge. Very simple. If suppose the conductor is small, it will hold less charge. If a conductor is big, it will hold more charge. Right? It depends on the area of the conductor. How much big the conductor is. Less area means less charge. More area means more charge. Correct? So that ability to hold the charge is known as capacitance. Capacitance is nothing but ability to hold charge is capacitance. Fine. So now from the definition we can understand, or from common sense, from logic, you can understand that capacitance is something which is the property of the conductor, the material. Right? The shape will decide how much charge it can hold. The size will decide how much charge it will hold. Okay? All right. The formula for this capacitance is Q by V. Just now I told capacitance is the property of that particular material, right? But here in this formula, it is depending on charge and potential. Actually, capacitance does not depend on charge and potential. Okay? How this formula has come, I'll tell you. See, what happens is usually when I tell this capacitor stores electrical energy, the thought what students get is maybe capacitance is something which will be having SI unit as joule, right? Or from this also, if you think electrical energy is stored by storing charge. If capacitors hold charge, that means maybe the SI unit of capacitance will be coulomb. But both are not true. Both are not true. The unit of capacitance is neither joule nor coulomb. If you see this formula, it is coulomb per volt. Correct? It is coulomb per volt. So how is this? Why this capacitance is equal to Q by V? See here. Suppose this is a conductor. It's a spherical conductor. It is not having any charge. I told capacitor is something which holds charge. So now I have to give it charge. Right? From where do we get the charge? Usually in physics, we get it from infinity. There is a place called infinity, a lot of charge is there. Okay. Now let's say for getting the first charge, small dq charge will bring and keep here. Okay. A time will come when a lot of charge will be there. A time will come when a lot of charge will be there. It will hold a lot of charge. Now, but for getting the first charge, when we'll get the first charge and keep it here, how much work will be done? Zero. There is nothing to oppose. But when I'll bring second charge, let's say this is dq charge which I have brought, work done was zero. When I'll bring another dq, I'll have to do certain amount of work. Why? Because this dq will repel that dq. Correct? I have to do work against this electric field. Fine. Now, for next charge, if I'll bring, let's say dq, I'll have to do more work. For next charge, if I have to bring, I'll have to do more work. Why I have to do more work? Because every time the potential is increasing. Initially, the potential was zero. When I had brought and kept one plus charge here, the potential has come. Now I have to work against this potential. Now the potential is more because the charge is more. I have to work more. Again, more charge will come, the potential will be more, I'll have to work more. Slowly, when a lot of charge will come. With charge, potential will also come. Are yes or no? That means to keep more charge, I need to do more work. So the charge holding capacity of this conductor depends on potential also. If potential is less, I can give it more charge easily. Now, while giving more charge, potential is also increasing. Now, if the potential has increased, potential is more. Now, for giving more charge, I have to do a lot of work. I also have a limited amount of energy. I can do a limited work. That means a limited amount of charge I can put until I can work against that potential. Correct? Charge holding capacity is depending on potential also. I hope now you got that feel. Now you understood why this formula, this capacitance is having Q by V. Okay. How much charge that particular capacitor will hold will also depend on the potential. Fine. C is equal to Q by V. I hope you got it. Potential and charge are having relation with each other. The more charge will bring, the more potential this will get. So further giving the charge will be a difficulty. We can do work and put charge. So every time we are putting more charge, potential is increasing. We are putting more charge, potential is increasing. Clear? Capacitance is equal to Q by V. Got the feel? Alright. Now, as I told, note C does not depend on Q and V. Now, just now again I explained that C is equal to Q by V. Again I am telling C does not depend on Q and V. C is the property of material and depends upon shape and size of the material and type of medium. Understand? Resistance is equal to V by I. 10th standard. When you heard resistance for the very first time, we got the formula of resistance, right? And if you remember, resistance is the property of the material. Correct? Every material will have different resistance, but still the formula for resistance is V by I. What does this mean? Does this mean that resistance is depending upon potential and current? No. It means if the potential will increase, the current will increase, keeping the resistance constant. If the potential will decrease, the current will decrease, keeping the resistance constant. Resistance is always constant. It is the property of material. Alright. The same way, capacitance is always constant. For any conductor, capacitance will be constant. Okay. To explain you this, I have a question also. You can feel this thing also. Before that, what is the unit of capacitance? Unit of capacitance. Capacitance is equal to Q by V, that is coulomb per volt. What is coulomb per volt? Coulomb per volt is farad. We represent it by F. Farad. Okay. You can note it down. Now, see this question. What do you understand by capacitance of a conductor is 3 farad? If I tell capacitance of a conductor is 3 farad, that means capacitance is equal to Q by V. What does this mean? 1 farad is equal to 1 coulomb per volt. So 3 farad means, okay, this was for F. 3 farad means 3 coulomb per volt. Are yes or no? This means if there is a conductor, if I give it 3 coulomb charge, 1 volt potential will increase. This means this. If I give more 3 coulomb charge, 1 volt potential will increase. This 3 farad means this. If I give more 3 coulomb charge, 1 volt potential will increase. Clear? Every time I will put 3 coulomb charge, 1 volt potential will increase for this particular capacitor, for this particular conductor. Like this, every conductor will have different capacitance, different charge holding capacity. Okay. Now if you see, I have given it 3 coulomb, 3 times. Total charge this conductor is having is 9 coulomb. Total potential this is having is 3 volt. 1 plus 1 plus 1. Still the capacitance is 3 farad only. Capacitance is always constant. Clear? So this charge and potential will keep on changing depending if charge is increasing, potential is increasing. If charge is decreasing, potential is decreasing. Capacitance will always be constant. Okay. So at particular instance, if you know the charge and potential of any conductor, you can tell the capacitance. Fine. Because the potential will be according to the charge only. I hope you got this. Now you felt capacitance is constant. It does not depend on charge and potential. It depends on material, on the medium, on the shape and size of the material. Now we'll understand this. See, spherical capacitor or spherical conductor. This is a spherical conductor. Okay. For this spherical conductor, if I want to write the capacitance, capacitance is equal to Q by V. Suppose this is having a lot of charge. A lot of charge it is holding right now. This charge is Q. At this time, the potential at the surface is V. Fine. The radius of this spherical conductor is R. C is equal to Q by V. So C is equal to Q upon, how much is V at the surface right now? KQ by R. KQ by R. Q and Q will be cancelled. R will go up. What is K? This is R by K, right? K is 1 upon 4 pi epsilon naught. 4 pi epsilon naught will come in the numerator, right? So this will be 4 pi epsilon naught R. K is 1 upon 4 pi epsilon naught. Now see this formula. Capacitance is depending on the radius of the sphere and epsilon naught, that is medium which is around. Correct? It does not depend on Q and V. Now did you understand it? Okay. Did you feel that? Fine. So now R is radius. I can write capacitance depends on size, correct? And shape also. This 4 pi is because it's a sphere, right? For parallel plate, the formula will be different. So shape and size. Another thing, capacitance depends on medium. Here it is air, that's why it is epsilon naught. All right. Capacitance depend on size, shape and size. And capacitance depends on medium. Now, next. If radius of a spherical conductor is 1 meter, find the capacitance. Okay. I have got two questions from which I want to explain why we do not use this spherical conductor in real life. In practicality, why don't we use spherical conductors? Okay. First, we'll do this question. If radius of a spherical conductor is 1 meter, find the capacitance. Radius is given to be 1 meter. Capacitance is equal to 4 pi epsilon naught R for a spherical conductor. So that means 4 pi epsilon naught 1. What is 4 pi epsilon naught? K is equal to 1 upon 4 pi epsilon naught, and that is equal to 9 into 10 power 9, correct? So 4 pi epsilon naught will be 1 upon 9 into 10 power 9. 1 upon 9, I'll write this side because below one more question is there. So from here, C is equal to 1 upon 9 into 10 power 9. 1 upon 9 means 0.11. So if I write 1.1, this 10 power 9, if it goes up, it will be 10 power minus 9. Since I have shifted this decimal also here, 10 power minus 10 farad. 1.1 into 10 power minus 10 farad. Just see the capacitance. It is of the order 10 power minus 10. So small, so small. If you see the radius of this conductor, this capacitor, it is 1 meter. You know how much is 1 meter? This much big, 1 meter. And if I talk about the sphere, it will be having diameter this much big sphere. This much big sphere, and the capacitance is of the order 10 power minus 10. So small. That's why this capacitor is useless. It is not a good capacitor. The charge holding capacity is very less. One more question you can see. If we want the capacitance of 1 farad, find the radius. Let's say this is 10 power minus 10 farad. If I want 1 farad, how much would be the radius? Now, capacitance is equal to 1 farad. Capacitance is 4 pi epsilon naught R. So now 4 pi epsilon naught R is equal to 1. From here, this is 1 upon 9 into 10 power 9. R upon 9 into 10 power 9 is equal to 1. R is equal to 9 into 10 power 9 meter. 9 into 10 power 9 meter. You know the radius of Earth? The radius of Earth? 6.4 into 10 power 6 meters. Correct? 6.4 into 10 power 6 meter. See this? 9 into 10 power 9. Sphere of radius bigger than Earth we need for capacitance 1 farad. Not possible, right? This kind of capacitor not possible. to get 1 farad we can never get from a spherical capacitor. That's the reason in reality, in practicality, we do not use spherical capacitor. Okay, a lot of changes came and then we got with a new kind of capacitor. We'll see in the next session. Fine. Next, energy is stored in a capacitor. So I'll tell from spherical capacitor, and the same energy is stored in all kind of capacitors. Okay. Now suppose it is a spherical conductor. Initially no charge is there. What we do, we bring charge from infinity, right? So first, when I brought first dq very small. Obviously, if I want to give it q charge, I'll not bring all the charge all at once and keep. Not possible. Slowly the charge will come. Slowly the charge will come. All right. First dq when came, the work done was 0. Next dq when it will come, the work done will be more than that. Next dq, the work done will be more than that. What I'm trying to tell is the work done is not constant. First dq is there. Then one more dq I brought, I did some work. Now 2 dq are there here. So if I bring one more dq, this 2 dq will repel. Let's say I did some work and I brought this dq here. Now here there are total 3 dqs. For bringing this fourth dq, this 3 dq is repelling. The work done will be more. Every time the work done is increasing. Every time the work done is increasing. Right? So work done is not constant, it is variable. Integration will come into picture. Okay. Before integration, let's see the story. Initially, let's say when there is no charge, at t is equal to 0. Charge on this q is equal to 0, correct? Potential 0. Capacitance C. Capacitance is the property of the material, correct? It does not depend on Q and V. Capacitance will be C. Next, at t is equal to infinity, when it is completely charged, let's say after a lot of time it is completely charged, okay? T is equal to infinity, the charge will be Q, potential will be V, capacitance will be C only. In the middle somewhere, when let's say some charge we have brought, it is not fully charged. In the middle at some time t, this q will be some q, small q. Slowly the charge is increasing. First charge came, second charge came, third charge came. Like this, at some time t, it is not fully charged. At some time t, let's say it is having charge q. dq, we are bringing and we have kept it here. Okay. So at some time t, there is a charge small q. At that particular time, the potential will be, let's say, small v. It will not be capital V, right? That is when the charge is q. So let's say at this time, the potential is also some V potential is there. Capacitance is same every time. Fine. For here, if you want to write capacitance, it is small q by small v. For here, if you want to write capacitance, it will be capital Q by capital V. But this capacitance will be same, right? Okay, so this is the story. At t is equal to 0, this is the story. Then slowly we are bringing the charge. At t is equal to t, q will be q, v is equal to small v, capacitance will be the same. At t is equal to infinity, when it is fully charged, q is equal to q, v is equal to same capital V, and c is equal to c. Now, as I told, for bringing this charge, the work done is variable, right? At time t, let's say the potential is small v, I have already told. Here on the surface, let's say the potential is small v. Infinity, the potential will be 0. V infinity is always 0. So now if I want to write the potential difference, V minus V infinity, that is equal to the small, at this time also, we are bringing dq only. At every time, at every instant, we are bringing dq, right? So at this instant, at t is equal to t, V minus V infinity, small v, okay, V minus V infinity is equal to dw by dq. This dq we are bringing, and for bringing this dq, the work done, small work done is dw. Okay, I hope you got this. So now V infinity is 0, so V is equal to dw by dq. correct? From here, dW is equal to V dQ. Very important. dW is equal to V dQ. From here we will derive the formula. Okay? It is at some time t. Now see, dW is equal to V dQ. I have to find out the complete work done. See, energy is stored in capacitor. What is the energy stored in capacitor? The work done by external agent is nothing but the energy which will be stored in the capacitor. Delta U is equal to W external is equal to delta U, that is U final minus U initial, correct? U initial, when there was no charge, U initial was 0. For the configuration, when there will be no charge, U initial will be, it is KQ square by R, correct? U initial will be 0. So U final or U potential energy on that capacitor, on that conductor is W external. That's the reason I am finding out W external. Once we get W external, that is nothing but the potential energy. Because whatever work I am doing, the same work I am storing in form of potential energy. Clear? So now I have to find this work. From 0 to W, this is from 0 to Q until it gets fully charged, right? So this integration will be W external, let's say, that is equal to V is K for this time. When Q charge is there, what will be the V? Radius is R. When Q charge is there, what will be the V? KQ by R. KQ by R dQ integral 0 to Q, correct? K and R is constant, K by R will come out. Integration of Q dQ is Q square by 2, that is Q square by 2, and integrating from 0 to Q. Fine. This will be K Q square by 2R, that is work done by external agent. Fine. If you want, I'll write down delta U is equal to work done by external agent. U final minus U initial is equal to work done by external agent. U initial here is 0 because initially for that configuration the charge on that capacitor was 0. So U final is equal to W external. U final is nothing but U. So that is U is equal to, let me write it here, U final. So U is equal to K Q square by 2R. Now see, this K is 1 upon 4 pi epsilon naught. So now U is equal to Q square upon 2 times 4 pi epsilon naught, and R is there. This 2 I have written as it is, K 1 upon 4 pi epsilon naught. See this. What is this? What is this? Capacitance of the conductor, right? Capacitance of the capacitor. So this will be Q square by 2C. The relation of potential, this is potential energy in terms of charge and capacitance. Q square by 2C. Remember this always. This no need to remember. What you have to remember is this always, because it is in terms of charge and capacitance. All right. Next. In terms of capacitance and charge, I already told U is equal to Q square by 2C. Now, in terms of capacitance and potential, potential means I have to remove this Q. How can I remove this Q? If I put Q is equal to CV. Remember the very first formula, capacitance is equal to charge per unit volt, Q by V. So from here, Q is equal to CV. That's what I have put. Here, just substitute Q is equal to CV. Now, this is something what I always remember. I don't know how I remembered, but Q is equal to CV, I always remember. Okay, I never get confused with this. Q is equal to CV. Q is equal to CV. Okay. Now, like V is equal to IR, the same way, Q is equal to CV. I have always remembered. So now CV, if I put here, This will be U is equal to C square V square upon 2C. C and C will be cancelled. This is half CV square. Half CV square. That is the formula. In terms of charge and potential, so now this capacitance I have to remove. For removing this capacitance, I can put capacitance as Q by V. So here if I put capacitance as Q by V, this will be U is equal to half Q by V, V square, V will cancel, half QV. Half QV, that is the formula. Okay, what I have put here is C is equal to Q by V, I have substituted. Okay. How do I get this? I have substituted 4 pi epsilon naught R by C. See here, what did I do? 4 pi epsilon naught R I have substituted by C, I got this Q square by 2C. Alright, easy? Okay. This is the energy stored in capacitor. Always, for any capacitor this is true. For all the capacitors this is true. Next. Problems with spherical capacitor I have already discussed. We are at the end of the session. We have already discussed what are the problems. First, capacitance is very low even for radius 1 meter. Radius 1 meter means this much big sphere, but still the capacitance was, how much was the capacitance? 1.1 into 10 power minus 10 farad. So less. So that is one problem. Second problem is energy is not bounded. Energy is not bounded. See here, if this spherical conductor is there, suppose there is a lot of charge I have given to it. Okay, due to this lot of charge, the electric field will be outwards. This electric field is not bounded. This is free. It is extended till R is equal to infinity. Till there it is extending. Right, this electrical energy, since it is, this electric field is not bounded, because of which the energy is not bounded. The energy gets spent just like that. See here how it gets spent. Easy to understand, just for understanding. Now suppose this electric field lines are till infinity. R is equal to infinity, right? Here at a very large distance, suppose obviously in its path till infinity there will be a lot of charges. A lot of charges will be around. Suppose there is a minus Q charge here. This will attract this, the charge on this capacitor will become less. Correct? Capacitance decreased again. Again see, if suppose there is a plus Q charge, this will spend its energy to repel this. Right? So energy is spent just like that. It is not bounded. A lot of plus Q charge will be there in repelling, in attracting, it will spend a lot of energy. Because the electric field lines are extended till infinity. Okay? So energy is not bounded. I hope you understood this. So because of these problems, we do not use spherical capacitor, we use parallel plate capacitor, which we'll be seeing in the next session. Okay, get ready for this session. Spherical capacitor is not important for boards. If you have seen it, very good, because for understanding it was important. Okay, but this is something which is important for boards. For this session you have to come. All right. If you understood today's session, if you enjoyed today's session, do press the like button, share it with your other friends who are preparing for their boards and competition, subscribe to our channel, and do not forget to click on the bell icon so that you never miss any update from us. Okay, you can visit our website www.v-learning.in. All the classes which we are providing you will get there. Along with that you will be getting lecture notes for each and every lecture. Slowly we are uploading it. How much is uploaded you can download and utilize that, and obviously slowly we are uploading it. Okay, we'll meet up in the next session. Till then, keep learning from V Learning. All the best.